Galaxies separated by millions of light-years move together in a silent, coordinated ballet. This is not science fiction, but the reality of our universe's grand design. We are about to explore one of cosmology's deepest mysteries: how galaxy groups form cooperative structures across these unimaginable distances. By the end, you will understand the invisible architecture that orchestrates the entire cosmos. We will uncover why the universe resembles a vast cosmic web, and what mysterious force guides galaxies in this slow-motion dance. What does it mean for our own place in this immense, interconnected system? This grand cosmic web is the ultimate expression of cooperation across the void. Its immense filaments trace the underlying blueprint of the universe, a blueprint written in the first fleeting moments of everything. To understand how this web formed, we must journey back to a time before galaxies, before stars, even before atoms themselves existed. We go back to the instant of the Big Bang. In that first unimaginable surge of energy, the universe was not perfectly smooth. It was filled with tiny, random quantum fluctuations, minute differences in density from one point to the next. These infinitesimal ripples were the seeds from which the entire cosmic web would one day grow. For hundreds of thousands of years, the universe was too hot and dense for these seeds to do anything but simply exist, trapped in a raging sea of light and matter. Then a pivotal event occurred, one that set the stage for everything to come. The universe expanded and cooled enough for atoms to finally form, releasing the light that had been trapped within. This moment, the release of the cosmic microwave background radiation, gave the tiny density fluctuations their first real chance to act. Gravity, the universe's great sculptor, began its slow, patient work. It gently pulled matter toward those slightly denser spots. Over hundreds of millions of years, this gentle tug organized the primordial gas into a vast, diffuse network of dark matter, an invisible skeleton upon which the visible universe would later be built. How did this invisible framework dictate the motion of galaxies we see today? The answer lies in the deepest gravitational connections. That mysterious director is dark matter, an invisible substance that makes up the bulk of the cosmos's mass. Think of the early universe as a construction site where dark matter formed the unseen scaffolding, the strong skeletal framework upon which everything else would be built. While ordinary matter, the stuff that makes up stars and planets, was buffeted by the intense pressure of light in the young universe, dark matter remained unaffected. It could silently and steadily begin to clump together under its own gravity. These gathering pools of dark matter created the first gravitational wells, deep pits in the fabric of space that would eventually draw in the gas to form galaxies. This is the true beginning of cosmic cooperation. Dark matter did not act alone, but it laid down the foundational rules, creating a gravitational landscape that guided the visible universe into place. Without this pervasive, unseen influence, those initial seeds from the Big Bang might never have grown into the magnificent structures we see today. So what is this strange substance that commands such power yet remains completely invisible to us? Dark matter's halos are not isolated structures, but are woven together into an immense and interconnected network. This cosmic web of dark matter acts as the universe's true superhighway, a system of gravitational pathways that links even the most distant galaxy clusters. The empty voids we see between galaxies are not truly empty at all. They are spanned by these tenuous filaments of invisible matter, creating a continuous scaffold that holds the entire structure together. It is along these invisible roads that the influence of gravity can travel, orchestrating the motions of galaxies separated by millions of light years. A galaxy does not simply wander randomly through space. It is flowing along the contours of this underlying dark matter landscape, guided by the gentle, persistent tug of the entire cosmic web. This is how cooperation is achieved across the void. A galaxy group in one part of the sky and another group far away can move in a correlated way because they are both connected to the same vast, dark matter backbone. Their motion is a coordinated response to the shared gravitational field they are all embedded within. It is a slow, silent conversation conducted not with light, but with gravity. So if dark matter provides the stage and the script for this cosmic dance, what force compels the visible galaxies to take their places and follow the cues? Gravity is the silent language of this cosmic conversation, a force that speaks across the void without a single word. It works not instantaneously, but through the deep, established pathways of the dark matter web. Think of it like this. If you are standing in a valley, the entire shape of the surrounding hills influences your path, not just the rock at your feet. In the same way, a galaxy nestled within a dark matter filament feels the collective gravitational pull of that entire immense structure. This is a form of cosmic cooperation that transcends the limitations of light speed. The gravitational field, shaped by all the matter in the filament, is already in place, a pre-existing landscape that guides motion in a coordinated way. This is the essence of general relativity in action, where mass tells space how to curve, and curved space tells mass how to move. The resulting dance is a slow, majestic response to a conversation that began eons ago. We see this cooperation most clearly in the universe's greatest gatherings, where gravity's influence is unmistakable. These galaxy clusters are the bustling metropolises of the cosmos, immense cities of stars where hundreds or even thousands of galaxies are bound together by their collective gravity. They are not random gatherings but form at the busiest intersections of the cosmic web, where multiple dark matter filaments converge. This creates a deep, shared gravitational well, a central hub that orchestrates the motion of every member. In a place like the Coma cluster, galaxies do not drift aimlessly. They orbit a common center of mass in a slow, stately dance that can take hundreds of millions of years to complete. This is cooperation on a staggering scale, a celestial society governed entirely by the unseen pull of its dark matter foundation. Within these dense environments, galaxies live in close quarters, leading to frequent and dramatic interactions. They swing past one another in gravitational slingshots, their outer stars pulled into long, streaming tails. Sometimes they even collide and merge in spectacular events that forge entirely new galaxies. This process, which astronomers call galactic harassment, is not destructive chaos but a fundamental mechanism of growth and change. It is how these cosmic cities evolve, with gravity acting as both architect and urban planner, constantly reshaping the galactic skyline. These clusters represent the ultimate expression of cooperative dynamics, where every member's path is dictated by the whole. Yet, this principle of interconnected motion extends far beyond these brilliant, crowded hubs into much quieter and more diffuse arrangements of galaxies. Far from the crowded metropolises of galaxy clusters, most cosmic citizens live in quieter, more intimate neighborhoods. These are the galaxy groups, the fundamental building blocks of the cosmic web's vast society. Typically home to just a few dozen galaxies, these groups are bound together by a gentle, mutual gravity, creating a local community where every member influences every other. Our own Milky Way is not an isolated island universe, but a proud resident of such a community, known as the local group. Here, we share our cosmic street with giants like the Andromeda Galaxy and the Triangulum Galaxy, along with over 50 smaller dwarf galaxies, all moving in a slow, shared gravitational embrace. The dynamics within a group are profoundly different from the chaotic rush of a massive cluster. Interactions are slower, more graceful, and far less violent. This allows for long-term relationships to form over billions of years. Galaxies engage in a continuous, stately dance, their paths weaving around one another in a display of gravitational cooperation that preserves their individual identities while still binding them into a single, coordinated system. This gentle environment is where galaxies can mature and evolve without the constant turmoil of disruptive collisions. Yet, these quiet neighborhoods are not isolated. They are deeply connected to the wider cosmos, often serving as feeder groups, sending their member galaxies along the dark matter filaments toward the hungry clusters at the intersections. This process raises a profound question about the nature of cosmic structure itself. How do these individual groups, these local communities, themselves become organized into the immense, continent-spanning patterns we observe across the universe? This cosmic landscape is defined by a breathtaking duality: the brilliant, dense threads of the cosmic web, and the profound, empty expanses between them. These are the filaments and the voids, the continents and the oceans of our universe. The filaments act as the universe's grand transit corridors, immense bridges of dark matter and galaxies that can stretch for hundreds of millions of light years. Along these vast highways, entire galaxy groups stream like celestial traffic, their motion directed by the relentless pull of gravity toward the massive clusters that form at the interchanges. This flow is not a random drift but a coordinated migration, a slow river of star systems following the gravitational contours of the invisible scaffold. Opposing these dense pathways are the voids, regions of stunning emptiness. These are not small pockets of nothing, but colossal spherical bubbles in the cosmic foam, some so large they could contain thousands of our Milky Way galaxies lined up end to end. Within a void, you might find only a handful of isolated, lonely galaxies, the rest having long ago been drawn out toward the denser filaments. The formation of this foam-like structure was an inevitable outcome of gravity's dual nature. It pulls matter together along the densest lines of the initial dark matter blueprint, causing it to collapse into filaments and nodes. Simultaneously, it allows the underdense regions to expand and empty out, as if the universe itself is breathing out in these vast spaces. This process creates a coherent architecture where every galaxy, every group, and every cluster belongs to a larger continent of matter, all part of a single, interconnected system. So what is the precise mechanism that guides this galactic flow, that ensures galaxies move in concert along these cosmic highways? The answer lies in a subtle but relentless pressure, a gravitational influence that shapes the very paths they travel. Our entire local universe is in motion, caught in a silent river of galaxies flowing toward an unseen destination. This grand cosmic drift, a phenomenon astronomers call a bulk flow, reveals that the cooperative structures we see extend far beyond the boundaries of any single cluster or filament. Our own Milky Way, along with our entire local group and thousands of other galaxies, is part of this immense stream, all pulled in the same direction by a colossal gravitational anchor known as the Great Attractor. This mysterious region, hidden behind the dense stars of our own galaxy's central bulge, represents an immense concentration of mass, a grand junction in the cosmic web, whose gravity reaches out across hundreds of millions of light years to guide our path. This is not a singular pull but the cumulative effect of an entire continent of matter, a vast overdensity in the cosmic landscape whose collective gravity tugs on everything in its vicinity. The existence of these bulk flows is profound evidence. It tells us that the universe's mass distribution is not smooth and uniform, but decidedly lumpy and structured on the very largest scales imaginable. Gravity's influence does not stop at the edge of a galaxy cluster. It seamlessly stitches together entire superclusters, creating coherent motions across volumes of space so immense they challenge comprehension. A galaxy participating in a bulk flow is not just orbiting its local group. It is also riding a far grander current, a slow river within the cosmic web that carries it along a path set by the gravitational landscape of the entire visible universe. This collective motion hints at a pattern of structure even larger than the web itself, an architecture of matter so vast we can only perceive it by tracing the subtle, coordinated drift of countless galaxies. What could possibly be massive enough to generate these continent-scale currents? And what do they reveal about the ultimate fate of our cosmic neighborhood? This very expansion of the universe itself holds a mystery that could reshape our understanding of the cosmic web. Astronomers call it the Hubble tension, a quiet but persistent disagreement over how fast the cosmos is growing. When we measure the expansion rate using the ancient light from the universe's infancy, we get one number. But when we measure it using stellar explosions in our modern, nearby universe, we get a slightly different number. They do not match. This is not a simple error, it is a fundamental discrepancy that suggests a gap in our knowledge. Perhaps dark energy, the force driving the expansion, is not constant but changes over time in ways we have not yet grasped. Or maybe gravity itself behaves differently across the vast, empty stretches between galaxy superclusters than our theories predict. This tension is a direct challenge to our models of cosmic evolution. The way galaxies cluster into groups and move along the web is not separate from the universe's expansion. It is deeply woven into it. The entire history of how those cooperative structures formed, from the first tiny ripples to the great filaments we see today, is tied to this expansion rate. A different expansion history would mean a different web, a different pattern of cosmic metropolises and quiet galactic neighborhoods. To resolve this puzzle, to see if our standard model of the cosmos needs a profound update, we must turn to a powerful tool that allows us to rewind time. We build entire universes inside supercomputers, running the clock back 14 billion years to watch the cosmic story unfold from the first moment to the present day. The digital universe awakens from a near-perfect void. Inside a supercomputer, billions of particles of dark matter and gas are born from a mathematical seed, their initial positions dictated by the faint whisper of the cosmic microwave background. This is a cosmological simulation, a universe in a box governed entirely by the unbreakable laws of physics. As the virtual clock begins to tick, gravity starts its patient work. You can watch it happen, the subtle tug that gathers particles into faint, wispy tendrils. Over billions of simulated years, these tendrils thicken into the grand filaments of the cosmic web, while the spaces between them empty out into vast, spherical voids. At the intersections, brilliant knots of light ignite as galaxies form, coalesce, and begin their slow, stately dance. Projects like the Millennium Simulation and Illustris TNG do not just create pretty pictures, they recreate the entire history of cosmic structure, from the first quantum ripple to the sprawling galactic metropolises we see today. They are our ultimate testing grounds. By running these simulations and then comparing the final result to our actual maps of the universe, we can check if our understanding of gravity, dark matter, and dark energy is correct. It is a powerful form of cosmic validation. The profound cooperation we see, the synchronized motion of galaxies across vast distances, emerges naturally in these digital worlds as a direct consequence of the physical laws we program into them. It is not an added feature, but a fundamental outcome. Yet this cosmic cooperation has a dramatic, even violent, side. The same gravitational forces that weave the web also orchestrate its most colossal collisions. The cosmos is a place of both gentle guidance and spectacular violence. When two galaxies are drawn together by their mutual gravity, they engage in the most direct form of cooperation imaginable, a merger that reshapes their very essence. This is not a chaotic demolition but a carefully choreographed, billion-year-long dance of creation through collision. As the galaxies first approach, their immense gravitational fields begin to pull at each other, stretching out long, shimmering arms of stars and gas. These are tidal tails, beautiful celestial ribbons that mark the beginning of a profound transformation. The galaxies do not slam directly into one another. Instead, they swing past in a series of ever-tightening orbits, each pass drawing them closer until their fates are irrevocably entwined. Within this swirling maelstrom, a miracle of cosmic recycling occurs. Vast clouds of interstellar gas, compressed by the gravitational turmoil, collapse to ignite millions of new stars in a brilliant firestorm of creation. This starburst phase can transform a quiet, settled galaxy into a dazzling stellar nursery, its light outpacing the combined glow of its original members. At the very heart of this frenzy, the supermassive black holes that likely anchored each original galaxy are stirred from their slumber. Fed by the inrushing gas, they become active galactic nuclei, blazing with light as they consume the bounty delivered by the merger. Eventually, after countless stellar orbits, the two galaxies lose their individual identities, their stars and dark matter halos blending into a single, new galactic entity. A major merger between two spiral galaxies like our Milky Way typically forges a giant, featureless elliptical galaxy, a smooth swarm of stars where the beautiful spiral arms are forever erased. This violent cooperation is a fundamental engine of galactic evolution. Our own Milky Way bears the scars of past mergers, the ghostly remnants of smaller galaxies it has consumed, and it is on a collision course with the Andromeda Galaxy, a future merger that will one day create a new colossal galaxy, Milkomda. Even in these most energetic of cosmic events, the underlying principle holds true. Gravity orchestrates a cooperative process that builds larger, more complex structures from smaller ones. But if mergers represent cooperation through direct union, what subtle forces govern the galaxies that never collide? Those that simply travel together through the void for billions of years. Even the gentlest gravitational handshake can leave a permanent mark. When two galaxies pass near one another without colliding, the side of a galaxy closer to its neighbor feels a stronger gravitational pull than the side farther away. This difference in force, a tidal force, acts like a cosmic sculptor, stretching and warping the galaxies over millions of years. The result is often breathtaking, long, graceful arcs of stars and gas pulled from their home galaxies, creating luminous bridges and tails that span the intergalactic void. These tidal tails are the ghostly signatures of a close encounter, a beautiful testament to an invisible gravitational conversation. Within the crowded confines of a galaxy cluster, these interactions become a constant fact of life in a process astronomers call galactic harassment. Here, galaxies swing past each other at tremendous speeds, their gravitational fields repeatedly plucking at one another. Over time, this relentless stirring can strip a galaxy of its precious star-forming gas, leaving it red and dead. It can puff up a sleek spiral disk into a bloated, disorganized elliptical shape. Each high-speed flyby is a subtle gravitational nudge, a small act of coercion that collectively reshapes the entire population, enforcing a kind of rough galactic conformity. This demonstrates that cosmic cooperation is not always a gentle dance. It can also be a process of persistent, long-distance influence that forever alters a galaxy's destiny. These silent interactions, these gravitational scars, are a permanent record of the interconnectedness of all things in the cosmic web. To truly read this record, to understand the scale of these interactions and the vast flows they are part of, we must answer a deceptively simple question. How do we measure the immense distances and precise motions of galaxies so far away? The faint light from a distant galaxy carries a hidden message in its color. When a galaxy races away from us, the very waves of its light are stretched during their long journey across the cosmos, shifting toward the red end of the spectrum. This phenomenon, redshift, is our most powerful tool for measuring the universe's expansion and the motions of its inhabitants. It works on a principle similar to the Doppler effect you experience with sound, where a receding siren drops in pitch as its sound waves are stretched. For light, this stretching translates directly into a color change, a cosmic fingerprint that reveals a galaxy's velocity. By measuring this redshift with immense precision, astronomers can calculate exactly how fast a galaxy is receding. This velocity, combined with Hubble's law which links speed to distance, allows us to place that galaxy at its correct location in three-dimensional space. It is as if every galaxy in the sky is calling out to us, and by listening to the subtle reddening of its voice, we can pinpoint exactly how far away it is and how quickly it is moving. This single measurement unlocks the ability to build a true map of the cosmos, not just a flat picture. But how do we use this tool to see the invisible architecture of the cosmic web? The answer lies in surveying the sky on an unprecedented scale. Projects like the Sloan Digital Sky Survey have spent years meticulously collecting the light from millions of galaxies, measuring each one's redshift to determine its distance. When you plot all these millions of points in a vast three-dimensional model, the hidden pattern emerges from the noise. The great filaments and walls of the cosmic web snap into view, along with the immense, empty voids between them. We can see entire superclusters of galaxies, and we can trace the slow, river-like bulk flows where thousands of galaxies move in concert. This redshift data is the primary evidence for everything we have discussed, the irrefutable proof that galaxies are not scattered randomly, but are organized into a coherent, cooperative structure of staggering size. It shows us the what and the where with breathtaking clarity. Yet, a perfect map of the ocean's currents does not fully explain the unseen force of the wind. But what if the universe's grand design requires no invisible actor? The cosmic web, with its intricate filaments and synchronized galaxies, might not be held together by dark matter at all. A radical alternative suggests our understanding of gravity itself is the piece that is missing. This idea is known as modified Newtonian dynamics, or MND. It proposes that on the vast, diffuse scales of galaxies, gravity does not follow Newton's familiar laws exactly. Instead, it gains a subtle extra strength in regions of extremely weak pull, like the outer fringes of a galaxy. This single tweak can beautifully explain why stars in a galaxy's outskirts orbit just as fast as those near the core. A puzzle that first pointed astronomers toward dark matter. For individual galaxies, MND is a stunning success, matching observations with an elegant simplicity. Yet the cosmos presents a much broader challenge. Can this modified gravity account for the immense cooperative structures we see, the galaxy clusters and the cosmic web itself? When tested against the violent collisions of entire galaxy clusters, like the Bullet cluster, MND faces a difficult hurdle. Observations show that the bulk of the mass, inferred from gravitational lensing, is separated from the visible galaxies, a result that seems to demand some form of dark, unseen matter. The theory also struggles to naturally generate the specific pattern of the cosmic microwave background, the very blueprint for the web, without incorporating additional, hidden components. This ongoing debate is far more than an academic disagreement. It places the formation of cosmic structures, from quiet galaxy groups to vast superclusters, at the very center of a fundamental question. What is the true nature of gravity? The correct theory must be able to explain it all. The gentle rotation of a single spiral, the frantic dance within a massive cluster, and the silent, cooperative flow along filaments that stretch across the observable universe. To see this cooperation in action, we need look no further than our own celestial backyard, where a long-term relationship is shaping the future of our entire local group. Our own galactic neighborhood offers a perfect window into this cosmic cooperation. The local group is our home within the vast web, a family of over 80 galaxies bound together by gravity in a relatively quiet corner of the universe. This is not a sprawling metropolis but a collection of cosmic villages, dominated by two great spiral cities, our Milky Way and the Andromeda Galaxy. Dozens of smaller dwarf galaxies swarm around these giants, their paths tracing invisible orbits sculpted by the group's shared gravitational field. The most profound story unfolding here is a slow-motion dance of destiny between the two largest members. The Milky Way and Andromeda are on an inevitable collision course, drawn together by their mutual attraction across 2.5 million light-years. In about 4.5 billion years, they will begin their final, majestic merger, a process that will ultimately forge a single, new giant galaxy. This future event is a local example of the hierarchical structure formation that built the entire cosmos, where smaller structures consistently merge to create larger, more complex ones. But the drama is not reserved for the giants alone. Look at the Large and Small Magellanic Clouds, two irregular dwarf galaxies that are close companions to our own. As they orbit the Milky Way, our galaxy's immense gravity is slowly pulling them apart. Long streams of gas are being drawn from them in a process called tidal stripping, feeding fresh material into the Milky Way's halo and fueling the birth of new stars. This gentle, continuous theft is another form of cooperation, a transfer of resources on a galactic scale that shapes the evolution of all involved. The local group is a microcosm, a nearby laboratory where we can watch the universe's fundamental processes of growth and interaction play out in real time. It demonstrates that the same forces weaving the grandest filaments are also at work in our own celestial backyard. And at the heart of all these dynamics, from the smallest dwarf's orbit to the largest galaxy's future, lies the subtle, pervasive influence of the cosmos's most mysterious component. While dark matter provides the cosmic script for gravity's dance, another far more mysterious force is rewriting the final act. Dark energy, a repulsive pressure woven into the fabric of space itself, now dominates the universe's energy budget. It acts as a cosmic accelerator, pushing the expansion of the universe to ever faster speeds. For billions of years, gravity held the upper hand. Its relentless pull allowed matter to collapse into filaments and clusters, building the magnificent cosmic web we see today. But as the universe grew older and more diffuse, dark energy's influence began to swell. Now, this repulsive force acts against gravity on the very largest scales, creating a fundamental competition that will decide the fate of all cosmic structures. This is not a battle of destruction, but a slow, inevitable reshaping. As dark energy accelerates the expansion, it makes the universe's background landscape increasingly steeper and more difficult to climb. This suppresses the formation of new giant structures, vast reservoirs of intergalactic gas that might have one day flowed into a growing supercluster now find themselves pushed apart, their potential for future cooperation forever lost. The cosmic web is still growing, but its growth is slowing, its future connections severed before they can even form. In the far future, this accelerating expansion could grow so powerful that it begins to tear the existing web apart. First, the bonds between superclusters would stretch and snap. Then, galaxy clusters themselves would become isolated islands. Eventually, even individual galaxy groups might be pulled apart, their gravitational bonds overcome by the relentless push of expanding space. The great cosmic cities would become lonely outposts in an ever-darkening and empty void. This cosmic tug-of-war between the attractive force of gravity and the repulsive force of dark energy is written into the very architecture of the large-scale structure we map today. The distribution of galaxy clusters, the sizes of the great voids, the subtle flow of bulk motions, all of these hold clues to the balance of power between these two fundamental opponents. So how do the galaxies themselves, the citizens of this vast network, communicate their condition within this cosmic conflict? Galaxies are far more than passive drifters in a gravitational stream. They breathe, they erupt, they actively sculpt their own destinies. Within their stellar nurseries and at their very hearts, titanic forces are at work that reach far beyond their own borders. This is the drama of galactic feedback, a process where a galaxy's own life cycle influences the cosmic web around it. When a massive star reaches the end of its life, it does not fade quietly. It explodes as a supernova, a detonation so violent it can outshine an entire galaxy for weeks. This cataclysm does more than create new elements. It unleashes a ferocious blast wave that heats the surrounding gas to millions of degrees and drives it out of the galaxy in a powerful wind. On an even grander scale, the supermassive black hole at the center of many galaxies can awaken from its slumber. As vast clouds of gas and dust spiral inward, friction heats the material to incredible temperatures, causing it to glow with the light of billions of stars. This active galactic nucleus can then power colossal jets and outflows that blast material across hundreds of thousands of light years. These are not just isolated fireworks. They are fundamental regulatory mechanisms. By ejecting gas, a galaxy effectively starves itself of the raw material needed to form new stars. This feedback process prevents a galaxy from burning through its fuel too quickly, ensuring a long, stable evolution rather than a brief, brilliant flash. But the story does not end there. The enriched material blown out by these winds travels along the cosmic web's filaments, seeding the intergalactic medium with heavy elements and potentially influencing star formation in completely different galaxies millions of years later. This creates a complex dialogue where the small-scale physics of a single star's death can whisper into the vast architecture of the cosmic web. How far back in time can we trace this intricate conversation between a galaxy's internal life and the growing structure of the universe? The light reaching us from the edge of the observable universe is an ancient messenger, carrying images from a time when the cosmos was in its chaotic infancy. With instruments like the James Webb Space Telescope, we are no longer just theorizing about this era, we are witnessing it directly. We see faint, crimson smudges that are not the majestic spirals of today, but the primordial building blocks of the cosmic web, caught in the act of formation. These infant galaxies are not scattered randomly. They are already lining up along the faint, invisible threads of the dark matter scaffold, proving that the universe's cooperative architecture began to assemble astonishingly early. We can now observe vast, swirling clouds of gas and young stars that are the progenitors of today's most massive galaxy clusters, structures that existed when the universe was only a few billion years old. This is a direct look back at the process of hierarchical structure formation in action, confirming that the same gravitational rules that govern our local universe were already weaving the cosmic web in the distant past. While the early cosmos was a more turbulent and violent place, filled with intense star formation and frequent mergers, the seeds of the grand cooperation we see today were undeniably present. These observations from the dawn of time naturally lead us to wonder about the opposite end of the scale, the largest and most immense cooperative structures that have had billions of years to fully mature in the modern universe. These superclusters are the continents of our universe, land masses of light and gravity so immense they defy easy comprehension. Within a single supercluster, you are not looking at just one galaxy or even one cluster, but a sprawling collection of thousands of groups and clusters, all loosely connected by the grandest gravitational geography. Our cosmic address places us within the Laniakea supercluster, a Hawaiian name meaning immense heaven. This structure is our home continent, a web of filaments containing roughly 100,000 galaxies, all flowing together in a shared direction. Picture a vast, slow-moving river system where every stream and tributary, every galaxy cluster and group, is drawn toward the same deep gravitational basin. For Laniakea, that great basin is a region known as the Great Attractor, an unseen concentration of mass that acts as the supercluster's gravitational heart. But here is the crucial distinction that defines these cosmic continents. Unlike a galaxy cluster, which is tightly bound by gravity and will remain together forever, a supercluster is not gravitationally bound as a single object. The space within it is still expanding, stretched by the universe's overall growth. The cooperation we see is not a rigid bond, but a shared drift, a common destiny imposed by the underlying landscape of dark matter. Every galaxy within Laniakea, including our own, is participating in this collective flow, a silent migration across hundreds of millions of light years. This reveals the ultimate scale of gravitational influence, a coordination so vast it governs the motion of entire clusters of galaxies as if they were single entities. So where does it end? Is there a natural limit to how large these coherent structures can become? A point where the cosmic web's cooperation finally breaks down. There is a limit to the universe's grand architecture, a fundamental ceiling on how large its structures can grow. Astronomers call this the end of greatness, a profound transition point in the cosmos. On scales smaller than this, we see the intricate, lumpy tapestry of the cosmic web, with its brilliant filaments and cavernous voids. But when we zoom out to distances beyond roughly 300 million light-years, that intricate texture begins to fade. The universe starts to look remarkably smooth and uniform in every direction, a vast, homogeneous sea. This is the cosmological principle in action, the foundational idea that on the very largest scales, the universe has no preferred location or special center. It looks essentially the same everywhere. This principle is not just a philosophical statement. It is a crucial boundary condition for the entire cosmos. It means that while gravity is a powerful force for creating local cooperation, its influence has a finite range. The relentless expansion of the universe, driven by dark energy, ultimately overwhelms gravity's ability to organize matter. The cosmic tug-of-war has a clear winner on the grandest stage. No matter how vast a supercluster like Laniakea appears to us, it is still just a local fluctuation, a single wave on a much larger and calmer ocean. This sets a fundamental limit on the size of any cooperative structure. There can be no superclusters bound together by gravity, no organization that spans the entire visible universe. The end of greatness defines the ultimate horizon for cosmic society. So, with this limit now firmly in place, how will these magnificent but finite structures face the far future? This accelerating expansion is slowly unraveling the cosmic web itself. Dark energy's relentless push ensures that the universe's grand collaborative project has a final act. In the far future, trillions of years from now, the great filaments of the cosmic web will be stretched thin, their gravitational bonds strained to the breaking point. The silent rivers of galaxies flowing along these dark matter highways will gradually slow to a trickle and then stop entirely, their shared journeys cut short by the ever-widening gulf of space. Galaxy clusters, once bustling metropolises, will become isolated islands, their light fading as they drift apart in an ever-darkening and empty ocean. One by one, all galaxies outside our immediate gravitational neighborhood will be pushed away so fast that their light can no longer reach us, redshifted into complete invisibility. The observable universe will shrink to include only the few remaining galaxies of our own local supercluster, bound together in a final, lonely embrace. This long-term forecast points toward what scientists call a heat death, a state where the universe becomes a cold, dilute, and featureless sea. The era of large-scale cosmic cooperation, of galaxies moving in silent concert, is not a permanent state of the universe, but a magnificent, temporary phase in its long history. This inevitable future raises profound questions about our own moment in cosmic time. Why are we here to witness this brief, brilliant epoch of structure and connection? And what are the fundamental mysteries we must still solve to understand the full story of our universe's evolution from a formless beginning to a structured present, and on toward this silent, distant end? The grand architecture of the cosmos is built upon foundations we cannot yet see. We have mapped the great rivers of galaxies and traced the outlines of the dark matter web. Yet the fundamental nature of its primary components remains one of science's greatest enigmas. What exactly is the dark matter particle that forms the cosmic skeleton? Why does dark energy push the universe apart? These are not minor gaps in our knowledge, but chasms at the very heart of our cosmological models. Compounding this mystery is the intricate role played by the universe's ordinary matter. We now know that the violent lives and deaths of stars, the fierce winds from supernova, and the colossal jets from supermassive black holes all pump energy back into their surroundings. This process, known as baryonic feedback, does more than just regulate a single galaxy's growth. It heats the intergalactic gas, pushes material around, and potentially governs how efficiently matter can flow along the cosmic web's filaments. The question is how profoundly these small-scale fireworks alter the large-scale structure of the universe itself. To move from speculation to understanding, we need a new generation of eyes on the sky. A powerful wave of new observatories is poised to give us that deeper vision. The Euclid Space Telescope, now on its mission, is designed to create a colossal, three-dimensional map of the cosmic web. It will observe billions of galaxies to measure the subtle way their light is bent by the gravitational influence of dark matter, an effect called weak gravitational lensing. This will allow us to see the invisible scaffolding of the universe in sharper detail than ever before. On the ground, the Vera C. Rubin Observatory's immense camera will scan the entire visible sky every few nights, creating a living, breathing movie of the cosmos that will catch fleeting events and track tiny changes in the positions of countless stars and galaxies. Following closely, the Nancy Grace Roman Space Telescope will perform wide-field surveys to trace the history of the universe's expansion with exquisite precision, probing the nature of dark energy. Together, these missions will provide a flood of data so vast it will transform our statistical understanding of cosmic structure. They will measure the shapes and flows of galaxies with such accuracy that we can test whether our theories of gravity hold true across the entire breadth of space and time. This is not merely about collecting more information. It is about reading the fine print in the story of the cosmos, deciphering the subtle interactions between the dark universe and the visible one. The quest to understand how galaxy groups form cooperative structures is, ultimately, a quest to understand the physical laws that govern everything. So what does this mean for our own fleeting presence within this immense, evolving network? The universe we observe is not just any universe, it is one capable of producing us. The existence of the cosmic web, with its delicate balance of filaments and voids, may be far more than a beautiful coincidence. It could be a fundamental requirement for life. Consider a universe that was perfectly smooth after the Big Bang, with no density variations at all. In such a place, gravity would have had no seeds to work with, and galaxies, stars, and planets might never have formed. The cosmos would be a vast, dark, and eternal sea of featureless gas. Now imagine the opposite extreme, a universe that was far too lumpy from the start, dominated by enormous, chaotic clumps of matter. In that violent reality, planetary systems would be constantly bombarded and torn apart by gravitational encounters, their orbits destabilized long before life could ever gain a foothold. Our universe exists in a narrow, habitable zone between these two extremes, and the cosmic web is the visible manifestation of that perfect, life-enabling balance. Our own cosmic address reflects this series of fortunate conditions. We do not live in the chaotic core of a massive galaxy cluster, where stellar densities and radiation levels would be hostile to complex chemistry. Nor are we adrift in the profound isolation of a deep void, where the heavy elements necessary for planets and life might be too scarce. Instead, we reside in a quiet galactic suburb, a member of a stable group within a larger supercluster. This specific location provides a stable, long-term environment, a safe harbor where a planetary system can mature over billions of years without constant disruption. This line of reasoning is known as the Anthropic principle. It suggests that the large-scale structures we study, the cooperative filaments and the clustered galaxies, are not merely objects of scientific curiosity. They may be an essential part of a chain of cosmic circumstances that allows for observers to exist in the first place. The very fact that we are here to map the web forces us to consider that our universe must have properties that permit our existence. Our cosmic address is not a random spot on a random map. It is the product of a specific and necessary set of structural conditions that run from the largest supercluster down to our local galactic neighborhood. When we synthesize everything we have learned, a profound picture emerges. The universe began with a specific set of initial conditions, tiny ripples that grew under the patient force of gravity, guided by an invisible dark matter scaffold. This process built a web of staggering scale and beauty, a network that orchestrates the motion of galaxies across billions of light years. Within this web, galaxies cooperate, collide, and evolve, their internal lives feeding back into the grand structure. And at the intersection of all these vast, cooperative processes, in a quiet corner of a specific filament, conditions align to allow for a tiny, pale blue dot to form, and for life to arise and look back upon the cosmic architecture that made its existence possible. The story of the cosmic web is, therefore, also our own story. This entire cosmic narrative reveals a profound and layered hierarchy of cooperation. It begins at the smallest conceivable scale, with the faintest quantum ripples in the newborn universe. Those infinitesimal seeds were amplified by the relentless pull of gravity, which used the invisible scaffold of dark matter to build a vast, three-dimensional architecture. Within this architecture, galaxies did not form in isolation. They were drawn into social units, first as small groups, then as immense clusters, all strung along the luminous filaments of the cosmic web. The force of gravity acts as the universal language, the silent communication network that allows a galaxy millions of light years away to influence the path of another. And set against this entire grand project of construction is the countervailing force of cosmic expansion, driven by the mysterious pressure of dark energy. This is not a static picture, but a continuous, dynamic process. The universe is a complex system where every level, from the smallest dwarf galaxy to the largest supercluster, is linked in a chain of gravitational cause and effect. The fate of a single spiral galaxy is inextricably woven into the evolutionary story of the cosmos itself. This deep interconnectedness, this revelation that cooperation across unimaginable voids is a fundamental rule of existence, stands as one of modern cosmology's most significant gifts to human understanding. Our journey through the cosmic web leaves us with a universe humming with silent connections. We have traced the invisible hand of dark matter sculpting the grand stage, and we have listened to the gravitational conversations that guide galaxies in their slow, cooperative dance across millions of light years. This is not a cosmos of isolated islands, but a single, breathing structure of unimaginable scale, built on a foundation of profound collaboration. To comprehend this is to see our own home, the Milky Way, not as a solitary empire but as one thread in an immense and glorious tapestry, its story inseparable from the whole. This understanding is both empowering and deeply humbling, anchoring us within a cosmic story far greater than ourselves. Yet for every mystery we unravel, new questions beckon from the darkness. The quest to fully understand these cooperative structures pushes our technology and our imagination to their limits, driving us to build ever more powerful telescopes and to run ever more intricate simulations. The exploration is far from over. If this voyage into the universe's hidden architecture has captivated you, there are endless more secrets waiting to be uncovered. Consider subscribing to continue